200th anniversary of the book written by Sadi Carnot, and that's why I decided to ask him and his wife to come here at Danzig and to spend 2 days in order we could discuss about the second law of thermodynamics. And today, Professor Kostic is going to give us a presentation which is going to start from Sadi Carnot reflections to challenges of the second law of thermodynamics. So maybe I just can say a few words on about you, okay? So Professor Milivoje Kostic is a Serbian-American expert in thermodynamics and emeritus professor of mechanical engineering at Northern Illinois University in the States. He is editor-in-chief of the well-known journal which is called Entropy, okay? And he graduated with the University of Belgrade, and he obtained a PhD at the University of Illinois at Chicago through a Fulbright Scholars. And as you can imagine, he has a huge number of professional awards and recognitions, and he is a member of several professional societies and scientific advisory boards. So, Milivoje, thanks so much for coming here in our school, and now the floor is yours.
Thank you for the invitation, and thank you all for coming to hear my presentation. And usually, before I start talking about energy, I demonstrate energy. I'm exactly today 72 and a half years old. And I will do something for you that you will remember, and maybe presentation you may or may not, and here it is.
Wow!
So they say, oh, you are a man who did a cartwheel, not like what you presented. Anyhow, thank you again to all, and we came to Nancy, and after being in Paris for 9 days, wow. It was very tiring, you know, using metro, a lot of stairs up and down to get somewhere. Here it's all nice walking, relaxing distance, and it's a nice place to be and probably to do education and have a life.
But you are wealthy. Yeah, I mean, you are in good shape.
Thanks to my wife. She's a good cook. I will use this remote.
Yes.
So, I was invited to give a plenary presentation at Carnot's Legacy in Paris, where so it was a three-day basically gathering, mostly a physicist. And I'm glad here I'm with engineering, I hope. My background is engineering. I finished even engineering middle school and mechanical engineering program at University of Belgrade, and master's and PhD engineering at University of Illinois. So it's all engineering, but I'm deeply interested in fundamentals, meaning in theory. And many people think I'm a theorist, but actually I'm more practical engineer or scientist. And I was associated with major national laboratories in the United States. They invited me to solve their practical problems. In Argonne National Laboratory, we were producing nanofluids, and they got, involved in problem, and they invited me through the summit to help them get over. And then at NASA in Cleveland, and at Fermi National Lab, and at many companies. So I'm mostly interested in solving problems. Is it this button or not?
Yes, the one.
Right or left? Or maybe
the
that's
right.
Yeah.
Yes.
Oh, okay. There is a delay. So thank you again. And I don't mind being interrupted. If you have an urgent question interrupt me, no problem. That's what I do on occasion. And I'm coming from Northern Illinois University, which is about 100 kilometers west from Chicago. It's a smaller city, about 50,000 people. I don't know how many Nancy have.
I know.
Over 100.
Oh, so you're big. And Jean Noel promoted me to editor-in-chief of Entropy Journal, which I'm not. I used to be editor-in-chief at Thermodynamics section when it was established within Entropy Journal, and I was the first one, and when I turned 70 2 years ago, I wanted to step away or aside, and they say, stay a couple more years so that we find someone, and I just finished it this year, recently. And Entropy Journal is running a special issue dedicated to Sadi Carnot's reflections, and deadline is end of the year, so whoever is interested may submit a manuscript there. And as I said, we need to be aware of complexity but make things simple. And we need to turn ideas into reality. And the objective is to motivate young people so that they are, continuing and improving on whatever was done before. And then, as I said, I'm equally theoretical and practical person. That's how we all should be. Synergy between the two is necessary to solve problems, and if we cannot solve problems, it means we really do not fully understand theory. And if we cannot explain something, it means we do not understand it. And if one thinks theory is boring, that means one is not really interested in understanding to solve practical problems. So I like to emphasize the synergy between the two. And of course, along the way are challenges, and we need to make that impossible to be passive. And thermoscience holds the key to provide vision and check and balance methods to optimize and innovate further. This is my energy pyramid. So energy actually started from heat engines, from coals, and then non-renewables along oil and natural gas are main energy sources nowadays, but we are now looking to basically make things renewable and sustainable, and then we're talking about solar, hydro, biomass, wind, geothermal. Actually, France is pretty good with nuclear, which is, in many ways, environmentally better than renewable, non-renewable energies. But at the top of the pyramid is energy conservation, efficiency. So whatever we use, if we are efficient, if we double efficiency, then we'll use half of it. And then it's more than that, because usually those renewable and sustainable energies are low density energies sources, and they are not enough hard to accomplish those old stuff. But if you make things efficient, then with half we'll do the same. And then we now go to the topic of my talk. It's about thermal science. It's about heat to begin with. Everybody knows what's heat. But along the heat comes, of course, temperature and entropy. So heat is energy, thermal energy, and it's equal to product of temperature and entropy, the way mechanical compression energy is product of pressure and volume. Exactly so. There is no, it's total similarity. So temperature and pressure and voltage and chemical potential are intensive properties. Intensive properties per unit of extensive energy. And extensive properties are now for mechanical energy volume, for temperature entropy. So entropy is very physical property. Some people say it's so complicated, you cannot define it, there is 1,000 definitions of entropy, but that's really people talking. In reality, entropy is as physical as any other property. After all, we engineers measure it and tabulate the values, and it has a unit. And I'm talking about the real thermal entropy, not about many other entropies which are, named as such, like information entropy, or some other entropies are just using similar tools, similar probabilistic and stochastic tools to calculate it, but it doesn't make them the same, or it's not the same physical concept. And now, this is important. If we have, unfortunately, this doesn't work, right? This works only on the wall, not on the screen.
The wall, yes.
So basically, I could come in.
Yes.
If we have a thermal particle moving and has its own kinetic energy, then if it is basically contained in some space so that it cannot move, its own energy will be converted to random fluctuations, and it must be conserved according to the first law of energy conservation, and it becomes, this should be subscript, Boltzmann constant times T. So it was mechanical energy, here it's a thermal energy, and it's the same energy in another form. And if we really look into the equation, we know that thermal energy is entropy times temperature. So this Boltzmann constant is actually entropy concept-wise, and it has unit of entropy. And I actually call it particle unity entropy, S1. So it's a particle unity, it's an entropy for one thermal particle. And of course, that's a new concept that I just named for this conference in Paris and here. But this is what it is. And this particle could be bounced back, for some time, and we got all of that random motion of a single particle, or we could look at many particles instantaneously, it's the same thing. They will be having their own distribution in space, and it is not going to be uniform. Everybody knows distribution of particle motion. We could look at ideal gas for simplicity, but similarly it's with liquids and solids, their own random, it's a basically some kind of a elastic motion of a structure of whatever substance it is. So that thermal motion is ubiquitous, it's unavoidable, that's the title of heat and entropy. We cannot avoid it. Everything is, disturbed and randomly move, and that's actually thermal motion. That's thermal heat, that's thermal energy, that's actually defines temperature and entropy and thermal conductivity and all thermal quantities. And we need to keep in mind that microstructure is non-uniform, but it is sustainable and it is perpetual forever if no external disturbances. So it's its own equilibrium. Its own equilibrium is this non-uniformity of particulate motion. But that represents our bulk equilibrium, which is macro equilibrium with uniform properties. So average of such motion is our constant temperature and equilibrium. And just to be aware of it, and then Maxwell will come with just a silly idea, could we use a Mach demon to separate those non-uniformities into non-equilibrium? That's a visual thinking, because that non-uniformity is thermal equilibrium. And if you like to make it different, that will become non-equilibrium. And you need an effort, you need the work to do it, and of course, you could then use work back in the reversible processes. So I like to maybe emphasize here something that many people are thinking or whatever. So we know there is a heat and work. So heat and everything else is work. But heat is that randomness, that structure that, you know, but when I say randomly, it's like a turbulence. It's still something that establishes its own, basically last longing existence on its own. So it is dynamic equilibrium, and basically that's very special because all other energy types dissipate into heat. And that's why heat is universal. So the non-equilibrium defined actually force and forcing. It's natural tendency to equilibrate itself, to force energy distribution and transfer so that they are uniformly distributed in their own space towards equilibrium. And in the process, basically, you transfer that non-equilibrium work potential into equilibrium without work potential. So all work potential is dissipated to heat, and along with heat goes entropy. So entropy is generated. And now that work, that's intensive property. That's because of a non-equilibrium, intensive non-equilibrium. And that's what Carnot said. We need a temperature difference to produce motive power. When Carnot was doing his things, energy conservation was not established. Even term, concept of work was not established. He didn't use work, he used motive power. And heat was believed to be conserved, like caloric. And basically, to change temperature, if you could now focus and pay attention to what I'm saying. Temperature, heat is transferred from high to low temperature. So, and heat will transfer between heat source and heat sink, and we cannot have heat higher than maximum heat source, nor lower than minimum heat sink without work. But with work, we could make heat at any temperature high or at any low. And that's intensive property. So we make non-equilibrium. Work makes non-equilibrium. And non-equilibrium is source of work now, backward. If we talk about reversible processes, then whatever you spend, you get it back. Reversible means without any dissipation, without entropy generation or production. So the only way to really change temperature outside the source and sink is with work. And after all, we get absolute zero temperature by expansion, since there is nothing below it, and we can't even get it. But anyhow, and then there is heating, and that work is isentropic, ideally isentropic. If it dissipates into heat, of course, you get entropy there and heat. And then there is that's intensity. That's a potential, that's a temperature for heat, for thermal. But then extensive property is entropy. And entropy is now entropy times temperature is heat. So you can't have heat without entropy. You cannot transfer heat without entropy transfer. Whenever we have heat transfer, we have entropy transfer, and heating is entropic process as opposed to working is isentropic. And then I was promoting basically terminology, thermal transformer. That's basically power and refrigeration cycles. It's like a power cycle to get work, or in reverse, it's a heat pump cycle to get heat. And then with refrigeration cycle, you could either move heat, which is refrigeration, or supply it, which is heat pump. It's the same process. And then I'm now trying to promote Carnot-Clausius equality. Carnot-Clausius equality. There is a Clausius equality. That's that integral of dq over t equals 0 for reversible or bigger than 0 for irreversible. Well known, that's the definition of the second law, integral definition, but it started from Carnot's basically reflections. Clausius worked it out based on Carnot's reflections, even though Carnot's reflections was based on a false premise, on a premise that heat is conserved. Carnot was claiming in his reflections that the same heat is coming in, going out, but because we lower temperature, such heat we extract work. And that's violation of the conservation of energy. So you get some extra energy as a work, even though the same caloric pass through. But that misconception was lucky one that helped Carnot basically do his work. He was comparing heat engines with water wheel, with a hydraulic engine. And he said, as water is falling from high to low elevation or from high to low pressure, same water, lower potential gives us work. Now if we do with heat, the same will get work. And we do. Heat engines were existence back then. But keep in mind, efficiency of those heat engines were smaller than 5%. If Carnot measure heat in and heat out, it will be about the same, because only 3-4% were taken as work, everything else is heat. And that's within experimental errors. So if you are to measure it, you would conclude that caloric is conserved. But once we improve the engines to extract 30%, then of course we got only 70 left behind. So there is many misconceptions with Carnot. First of all, Carnot efficiency 1 minus T0 over T heat source was not done by Carnot, because that efficiency includes conservation of energy, where caloric is not conserved. And it is based on absolute temperature, which were not known by Carnot. They were established as a concept by Kelvin in 1849, I believe. And then maybe Kelvin proved it through ideal gas, not in general. And Clausius proved Carnot efficiency in general. But if you think about it, Carnot proved, and that's the most important things by Carnot, he proved by contradiction impossibility that all efficient